Right now, as you watch this video, a lithium-ion battery is on fire. And somewhere in the Atacama Desert of Chile, an ancient underground water system that took 10,000 years to form is being pumped dry so you can own an electric car. The global shift to clean energy was intended to end our reliance on foreign fuel. Instead, it created a new geopolitical bottleneck. We traded a dependency on the Middle East for oil, for a dependency on the Lithium Triangle, a remote, high-altitude region straddling Argentina, Bolivia, and Chile, that holds over half the world's accessible lithium. To extract this metal, mining companies drill into ancient underground aquifers and pump billions of liters of water to the surface, leaving it to evaporate under the desert sun for up to 2 years. In the Atacama, water is extracted thousands of liters per second, faster than it naturally returns to the system. The salt flat is physically sinking, and indigenous communities are losing rivers that sustained their agriculture for centuries. This chart tracks battery-grade lithium carbonate. Between 2010 and 2020, the cost was a near flat line. Then, as electric vehicle demand outpaced the slow extraction process, the price skyrocketed from a few $1,000s a ton to roughly $80,000 by late 2022. Raw metals make up nearly 60% of a battery's total cost, meaning this supply shock made electric vehicles more expensive, not less. To make clean transport affordable, researchers in Shanghai had to find a chemical alternative that bypassed the lithium triangle entirely. They found the answer in element number 11, sodium. It is the 6th most abundant element on Earth, harvestable from the salt in every ocean on the planet. It is thousands of times more common than lithium and effectively free. To make sodium work, engineers relied on a shared mechanical principle. Every battery is a rocking chair. When you charge it, tiny charged particles called ions rock from the positive electrode through a liquid chemical conductor called the electrolyte over to the negative electrode. When you use that energy, the ions rock back, creating an electrical current. But sodium chemistry has a specific physical flaw. A sodium ion is much larger than a lithium ion. When these bulky ions try to squeeze into a standard negative electrode during charging, they cause the material to generate gas bubbles. Over hundreds of cycles, this bubbling would physically destroy the battery's internal structure from the inside out. It took a decade of research and nearly 10 billion Chinese yuan for scientists at CATL to engineer a new, porous form of hard carbon that could accommodate these larger ions. By removing this physical barrier, they transformed sodium into an industrialized power source built on a cheap, infinite material. In the winter of 2025, 67 different electric vehicles were lined up on a frozen lake in Yakeshi, Inner Mongolia. Temperatures here regularly reach -40 degrees Celsius. It was the largest and most brutal EV cold weather test ever conducted. The results exposed why lithium fails in the cold. When temperatures drop, the liquid electrolyte inside a lithium battery thickens and turns sluggish, like cold honey. The lithium ions struggle to move between the electrodes, causing the battery's internal resistance to spike. In these extreme conditions, premium lithium vehicles lost up to 65% of their driving range. Sodium-ion batteries utilize a different internal chemistry. They use ester-based solvents, compounds like ethyl propionate, which remain highly fluid and mobile at temperatures as low as -50 degrees Celsius. They don't turn into honey. Sodium's large physical size actually becomes an advantage here. Because the ion is bulky, it forms weaker bonds with the surrounding liquid molecules. This means it takes less energy for a sodium ion to break free and start moving, allowing the battery to maintain near full power while lithium cells freeze up. Retaining over 90% of capacity at -20 degrees, sodium eliminates winter range anxiety. For drivers in Canada, Norway, and northern China, electric mobility remains fully viable through the coldest months of the year. Cold weather is an inconvenience, but battery fires are a safety crisis. To test for catastrophic failure, engineers use the nail penetration test. They drive a steel nail directly through an active battery cell to simulate a violent collision or a manufacturing defect, creating a massive short circuit. When the nail pierces a premium nickel-manganese-cobalt-lithium cell, the battery undergoes thermal runaway. Temperatures instantly exceed 600 degrees Celsius, often detonating the cell and ejecting shrapnel. Even safer lithium iron phosphate cells erupt into dense clouds of toxic gas during this test. When engineers drove the same steel nail through a fully charged sodium-ion cell, there was no fire and no explosion. A small vent of harmless gas was released, and the battery simply continued to deliver stable voltage output while fully impaled on the nail. The safety is driven by physics. The larger sodium ions create higher ionic friction inside the cell structure. When the nail creates a short circuit, the sodium ions migrate toward the puncture site, but they move so slowly that heat generates gradually. The liquid electrolyte never reaches its ignition temperature. Removing the risk of catastrophic fires protects densely populated cities and simplifies logistics. Sodium batteries can be completely drained to 0 volts and shipped across oceans without the safety hazards and high costs of transporting volatile energy storage. This science has already reached the road. The Chang'an Nevo A06 is a mass-produced vehicle that proves sodium-ion technology is ready for global markets. To solve sodium's slightly lower energy density, CATL engineers designed the AB pack. Instead of choosing one chemistry, they integrated sodium cells directly alongside traditional lithium cells, interlocking them like bricks within a single battery pack. A centralized battery management system intelligently routes power between the two chemistries. If you need hard acceleration on a freezing morning, the software pulls from the sodium cells. Once you are cruising at highway speeds on a warm afternoon, the lithium cells provide the deep energy reserves. This hybrid architecture delivers a virtually fireproof, weather-resistant electric vehicle with a range of over 500 kilometers. It is currently hitting the market at a starting price of approximately $15,400 US. By fusing these two chemistries, engineers have produced an electric vehicle that matches the performance of lithium at a much lower cost. A 500-kilometer EV priced like a used petrol car puts the dominance of the internal combustion engine at risk. The true barrier to clean energy has always been economic. Nations in the developing world, already struggling with high fuel import bills, were priced out of the lithium supply chain. In Pakistan, where millions rely on imported oil for transport, the high cost of lithium batteries made a clean transition nearly impossible. But Pakistan holds a domestic solution. The Kelra salt mine contains one of the largest rock salt reserves on Earth. Instead of importing expensive lithium, Pakistan can extract battery-grade sodium directly from its own soil to build a domestic storage industry. To bypass the lack of expensive fast-charging networks, engineers developed choke-a-swap stations. Instead of plugging a car in for an hour, drivers pull into a facility that works like a vending machine, sliding out a depleted sodium pack and slotting in a fully charged one in 3 minutes. Because sodium batteries are chemically stable even when completely empty, these depleted packs can be densely stacked and stored inside these swap stations without the fire risk associated with lithium. By removing the need for a rare, geographically restricted metal, sodium democratizes energy storage. The key to a clean future was never buried in the mountains of Chile. It was sitting on our dinner tables.